and welcome to a new session of Graviticulas. Our speaker today is Pedro Urrejola. Pedro graduated and did his master in theoretical physics at Pontificia Universidad Católica de Chile. Then he did his PhD in experimental particle physics at Johannes Gutenberg Universität in Main, Germany. During his career, Pedro has always been involved in research and education. He was a professor at Universidad Mayor. Then he was the physics branch and laboratory coordinator for the mathematics, physics and statistics nucleus NMFE. Pedro's main research line is experimental particle physics. He has done supersymmetry searches using the Atlas detector. He was also part of the level 1 Atlas calorimeter upgrade, where he developed and tested jet energy scale corrections and even simulations. Nowadays, Pedro works as a postdoctoral research in the Sapphire Millennium Institute, where he's dedicated to the calibration of new muon detector together with a search for physics beyond the standard model in final state, including muons. So we would like to invite Pedro now to tell us all about using muons to search for physics beyond the standard model with the Atlas detector. So Pedro, please, we are all yours.
Okay, thank you for the presentation, Sebastian. So, yes, so I have joined recently Universidad Católica and the Sapphire Institute. So I'm starting doing research. I was kind of out from research for a couple of years. So in this talk, you should expect a brief overview on particle physics, and then at the end, more or less what I'm planning to do and what I'm starting to do and what I'm doing right now. Okay, so first, so the overview, you will just get a brief introduction to the standard model. I hope this is not too basic for everybody, but I know that even for people coming outside, so coming from physics, but outside particle physics, some of this stuff might be rusty at least. So then I will stop a bit on the muon and its properties, then a bit of physics beyond the standard model, to move then to the experimental setup with the LHC and the Atlas detector, the Atlas upgrade during these years of shutdown, and then a bit on the muon detectors, the calibration of the muon detectors, and possible prospects or studies for searching physics using muons, to finally go to a summary. So the standard model, I guess most of you have seen already this table. So this is the table that includes our particles included in the standard model, and also the interaction fields between them. So the standard model is the most accurate explanation for 3 of the 4 fundamental interactions. So, you know, electromagnetism, weak interactions, and strong interactions. So the standard model does not include gravity. It has a Laurent invariant Lagrangian, and also the Lagrangian is invariant under the SU3 times SU2 times U1 gauge symmetry group. So here there are some sub-indexes, so C, L, and Y. So this is for color left, representing kind of chirality of the particles, and Y, the hypercharge. So this has completely, this sub-index have to do with how the interaction particles or the gauge bosons actually couple to the matter particles or fermions. So you have 3 generations of matter particles. You can see them here from left to the right, the first generation and the most light generation in mass of all of them. So here you see the numbers of the particles, the mass, the charge, and the spin. So these are numbers that comes with the particles, so are intrinsic to the particles and have nothing to do on how they interact. So you can see that moving from the first to the third generations, the masses goes up, while the other quantum numbers, so for example, charge and spin, remain unchanged. So the only difference between the generation is the mass. So we have 4 gauge bosons. So the gluon, the photon, the Z boson, and the W boson, which are interaction particles. So I will also explain that a bit in a few slides. So how these particles interact between each other, they interact via forces or interactions. So these are the three interactions. So the mediators of these interactions are these particles here. So for example, the strong interactions are mediated via the gluons, weak interactions via W and Z, and electromagnetic interactions via photons. And finally, typically, I would say last but not least, you have the Higgs boson. So the Higgs boson was initially just a theoretical contour of how the particles can have a mass, both gauge particles and fermions. And was actually finally discovered in 2012. So now it's completely like filling the standard model with the discovery of this boson. And in a very reduced way, we could say that the standard model Lagrangian can be written like this. Of course, all of this is just a very pictorial, I would say, simplification of the full standard model Lagrangian. So you will have in the first term all the gauge interactions between all the gauge bosons. Then you will have interactions between the fermions and the gauge bosons. So here phi is the fermions, and the covariant derivative includes the different vector fields. Then you have the gauge with the Higgs interactions, gauge bosons with Higgs interactions that also give mass to some of the gauge bosons. Some of these terms are responsible for giving mass for the gauge bosons. Then you have the Higgs self-interactions and also mass terms for the Higgs, of course, always after electroweak symmetry breaking that I will also discuss briefly. Then you have the famous Yukawa coupling that couples Higgs bosons with fermions. So you have interactions of the Higgs boson with the fermions, and also the masses for the fermions, and the Hermetic conjugate just to include antimatter for these same interactions and mass terms. So it is very important how these particles interact between each other. So as you can see, for example, for gluons, it's quite easy. They only interact with themselves. So this means a closed loop. And they also only interact with quarks. So gluons interact with color particles. So this is another thing that the quarks have. The quarks have a third quantum number called color. It has nothing to do with real color, but it's just a way to explain that there are three main colors that mix between each other. And the only particles that interact via strong force are particles with color. Then, for example, for the neutrinos, so you see here so you already know that the proton is made of up and down quarks. So these are the valence quarks for the proton and the neutron, and the atoms will have an electron. So these three are the most usual fermions that we are used to. So these involving proton and neutron, and the electron that would orbit around them in atoms. But you also have these like partners of these fermions that are called the neutrinos, which are in the standard model considered as massless particles. You see, and also they have no charge. So as you see here, for the mass parameters, you just have upper limits. You know that these have to be less than those values, but actually the mass is unknown, and the standard model was built thinking that the neutrinos were massless particles. So after it was built, we have seen evidence for neutrino oscillation, and thus for neutrino masses. So this is one of the possible problems that the standard model has. And one other important thing is that weak interactions, so mainly involving W, also was said, but W bosons. So these are the only forces that or interactions that neutrinos see. So you see neutrinos only interact with weak and set bosons. They do not interact directly with photons, neither with gluons. So they only interact with the other matter particles via weak interaction. So this is very important. This is why it is very hard to, for example, detect them, as they interact very weakly with regular matter. So then the rest of the particles, so the leptons and the quarks, so everything you have here and everything you have here, reduces all the quarks, reduce it into just one Q, interact with photons and with the weak bosons, and everything also interacts with the Higgs boson, except of course for the photon and the gluons that are neutral in charge. So so electroweak symmetry breaking. So as I said, this was a theoretical first introduction, this concept to the standard model as a way to give mass to most of these particles, so to the quarks and also the leptons, the massive leptons and the gauge bosons. And this was introduced doing a parallelism, or this you can think as at some point you have this scalar field, the Higgs boson, which has a potential that it has its minimum at 0, but after a few seconds, or I don't know, no, it actually very few microseconds after the Big Bang, this symmetry is broken, and then the lowest value of the potential is not fixed at the value 0 of the field itself. So you see the minimum, it has actually, this has an infinite 0 points here, because you can think this as a two-dimensional potential. And the fact that this field acquires a vacuum expectation value, it means that all these particles now see or interact with these bosons, and these interactions will give mass terms to the particles thanks to the electroweak symmetry breaking. So as I said before, in 2012, the Higgs boson was discovered. So the first images here is from the discovery. Here you have Higgs, Englert, and people involved in the theoretical introduction of the Higgs boson in the CERN auditorium. And here I put a couple of plots, for example, for the Atlas detector. You see here the points are the data in very specific 4-lepton region. So this is the Higgs boson decaying via 2 sets, and each set decaying to 2 leptons each. So you can plot the invariant mass of the 4 leptons, and you can see here in red and in purple backgrounds, the most important backgrounds for this possible signal of protons colliding and then having as an output 4 leptons. So the main background here would be Z plus Z, TT bar, and also 2 sets. So diboson production. And then you see here that in this region you have more points in data, and here you see that this is coherent with this signal, which is actually having a Higgs boson. So these points are fit better the existence of a Higgs boson. So here you can see additional plots. So this is for CMS. Again, you see the main backgrounds in green and light blue. So you actually, green, you cannot see much. And here you see extra amount of data on this region that is consistent with the existence of a Higgs boson of mass near 125 GeV. The same you can see here. So this is instead for a Higgs boson decaying into 4 leptons, decaying into 2 photons. And you can also see here this little bump that in the plot down here we have normalized just to see the effect of that bump. So we normalize the background to say like this. And you can see here that there's a clear indication of some additional particle here. So 10 years after, so this was actually 4th of July, 2022. This was this week. We have the 10-year anniversary of the Higgs boson discovery, and at this moment, the two main collaborations, so Atlas and CMS, present their latest results for Higgs mass, at least. So I'm trying to put a possible similar plots, so you can see here with much more clarity, and we hope, because we have now more data. You can see here was not much data on these plots, but here we have more luminosity, more collisions. We have more data, so we can see a much clearer shape of the Higgs bump, to say like this, near 125 GeV. You can see here, this is an overview or a resume of the different searches. So Higgs decay into 4 electrons, or 2 electrons to muons, 4 muons, 2 muons to electrons. So again, to 4 leptons. And here you have the combined results for run 2, and down here you have the combined results for run 1 plus run 2, finding a mass of 124 plus minus 0.18 for the Higgs mass. And the same you can see for CMS. So CMS was not running over the full data set for the last years, so in a reduced data set, but in the same way they can have very similar results, and you can see that they find a Higgs mass of 125.38, so similar values for the Higgs boson mass. So what about muons? So muons were first discovered from cosmic rays in year 1936. So for people actually outside science or particle physics, this might seem like a very old date, because probably they have not even heard about muons, but actually muons are here since quite a lot of time. In a few years will be already 100 years. So this was the first particle discovered that did not belong to the typical atom. So it was not a proton, a neutron, or an electron. So this was the first particle outside these groups. And they discovered it because it has a very distinctive curvature when they were measuring cosmic rays within a magnetic field. It did bend a bit less than electrons and a bit more than protons. So it was kind of between. At some point they thought it was a meson, that it was not fundamental, but later results have said that this is actually a fundamental particle that is very similar to the electron. It has the same quantum numbers, but it is just more massive. So it has mass that it's around 207 times the mass of the electron. So this means that high energetic muons are minimum ionizing particles. This is called MIPS. And why is this? Because Bremsstrahlung, so the radiation of light by accelerated charged particles, it is proportional to the mass of the particle. So actually, you can see here in the plots for the energy of an electron. So the electron already having an energy closely to, I don't know, 20 or 30 MeV. The Bremsstrahlung starts to being more important, loss of radiation compared to ionization processes. So the photons, the electrons, if they are very energetic, they will just lose a lot of energy through Bremsstrahlung. But for muons, you have a larger range here. So the point where these two radiations are the same, it's a higher number for the muon momentum at least, and you will have a large range of energetic muons that actually lose very small amount of energy. So these muons, at least for example on the LHC, they have these amounts of energy, so they will just travel through the detector without being stopped. They lose very few energy when interacting with the regular matter that we have in our detectors. So this muons is not stable particles. It has a 2 × 2 microseconds mean lifetime, but this for us is actually long. So this means that at these velocities close to the speed of light, the muon will actually decay once it has passed, for example, a particle detector. So we will see the muons traveling through the detector before they decay. And the typical decay of a muon is to an electron and an antineutrino, electronic antineutrino plus a muon neutrino. So you can see the typical decay of a muon. If you think time goes up, the muon comes, it emits a muon neutrino and a W boson, which will decay very quickly into an electron and to an anti-electron neutrino. So, as I said, the standard model is one of the most, or even the most precise models to measure and when measuring these fundamental interactions, but of course there is a limit for it. So first of all, it does not include gravity. So this is a huge question. How could we include gravity in a more unified theory? We also have the hierarchy problem, which means why is the Planck mass so much bigger than the weak scale, or also the matter-antimatter asymmetry. So we kind of think that there should not be any difference between matter and antimatter, but somehow after a few micro picoseconds from the Big Bang, this was lost, and then there seems to be more matter than antimatter in the universe. Of course, as I also tell you, neutrino masses and oscillations. So we have measured that neutrinos oscillate. So this means that neutrinos are made of different combinations of neutrinos. So here you can talk about neutrino 1, neutrino 2, or neutrino 3. And these neutrinos are a mix of the electronic, the muon, and the tau neutrino. And as these muons travel, this composition changes. So they travel oscillating the amount of each type of neutrino they carry. So by measuring some of these neutrinos from atmospheric experiments, and also from experiments from neutrinos coming from the sun, they have actually said and measure the difference of mass that these should have. So if they oscillate, they should have a mass, and they could evaluate the difference of mass between the 1, the 2, and the 3 neutrinos. So in this order, the M3, the third neutrino should be heavier, but of course you could do something different. And then there are different plots for this, but I just want to give you the idea that we know this difference of mass, but we don't know the exact value here. So what would be the mass, for example, of the first neutrino? So we don't know the masses of the neutrinos, but we know that they should have masses, and we know that there are some difference of masses between them. So another limit of the standard model, or maybe not say limit, or question maybe if there is actually gauge coupling unification. This is to think that maybe at some high energy, all the interactions are just cannot be told one from another, so that they will just get together to one unified interaction. And of course, we have the dark matter, which is actually a much more real problem, I would say, or limit, than the previous one, that it's, I would say, more mathematic, or maybe has to do with how ordered you want your theory to be. But in the case of dark matter, actually, we do have problems. For example, here I have a plot of the Ballet cluster. So here you have superimposed two images. So these were two clusters of galaxies that passed one through another. So you are just seeing this as it is after the, I would say, collision, but it's not maybe a collision. So they just passed by one through the other. And you can see here in the pink color, in pink color, this is most of the baryonic matter coming from the hot gas of these two clusters of galaxies passing through, and this we obtained from X-ray telescope. But then in blue, you see calculations from gravitational lensing on where should the concentration of the mass be. And you see that just from these results, it appears that this blue have passed more easily, while the pink one kind of gets stopped. So these two things collided, then the blue things apparently just passed through, while they actually, most of regular baryonic matter interacted with each other, and it kind of stopped. So this is why it's kind of getting behind. So this is a clear information that there is something that we are not looking at, and that we cannot see here from the cosmic rays, and it is passing through kind of without seeing each other. So this almost passed without losing any energy. So this is a clear indication that there should be here some amount of matter because of gravitational lensing that we are actually not able to see. There are other explanations from experiment for dark matter. So for example, you see the velocity of the stars in galaxies, and you see, for example, this dotted line is the expected only from the visible disk, and here are the dots from experiments. So you see that there is apparently a very huge difference between these two, and these have been proven to that if you have some matter there that you cannot see, actually the two curves fit much better. And then you have dark energy that I will also not talk so much about it, but from all the matter that we know, ordinary matter takes only roughly 5%, and then you have apparently 27% of dark matter, and all the rest is dark energy. So this is actually some very interesting field of research, as there is not much that we know there. So how can we tackle all these problems? So there are many models of physics beyond the standard model. You can see here kind of a typical drawing that I have seen that I like, that I put here. So you have like this soup of different ideas. So you have sectors that have not yet been thought of, or dark matter in some places, hidden dimensions, genome mediation, flavor, supersymmetry, anomaly mediation, flavor, quantum dimensions, extra dimensions. I don't know. There are many different theories that you could try to use to fix those problems, string theory. But lately, due to lack of evidence, at least from the LHC and the modern accelerators, some of these models are disfavored. So at some point, you could think that some model was okay, but then you realize that your data is putting him into a corner, and maybe the parameter space is every time getting smaller and smaller. At some point, you can also rule out some of these models. For other models, as I said, you can put constraints to them. So this is typically used, for example, for supersymmetry. You don't find any clear signals of supersymmetry, so you can constrain a bit the huge free parameter space that SUSY has, and then you can say, okay, if SUSY exists, it should not be like this. Because if it should have been like that, you could have seen evidence on the detectors. So there are other models, for example, that as nowadays there are lack of observables. So maybe I could say string theory could be here, but maybe in the future they could have some interesting observables, or we could actually tell if some results from experiments or even observations can tell between one theory or the other. So latest results on particle physics, on experimental particle physics, have shown very interesting hints of new physics in the flavor sector. So here, for example, I showed this plot. So this is the double radio of the branching fraction of a B plus decaying to a K plus and two muons over the same decay, but via the Jape side, and divided by the same, but instead of muons, electrons. And as you might know, as I said also before, the quantum numbers for muons and electrons are the same except for the mass, and then the coupling constants of the electrons to the gauge bosons are all the same. So this should not happen. So the ratio should be close to 1. And LHCb have shown this huge, sorry, this move. Oopsie, there. Actually, here is cut it. I don't know why this moved. So here you see one of the points for Babar experiment, and now LHCb has their new result. They have shown previous results also near here. So where you see a difference between the same decays going to muons and going to electrons. So this is a clear hint for possible lepton flavor universality violations. So this means that maybe the weak interactions or the Higgs interactions to fermions, or in this case leptons, should not be universal. So this is very interesting hints to look at. And also this year on April, CDF2 showed their most precise to the date W mass measurement, and you can see it here. So here you have the standard model expectation, which is here, and you see that the error bars on this measurement are quite small. So they did a lot of efforts trying to reduce systematic uncertainties on these results, as they always do in this just standard model analysis, because they are just searching for a standard model particle, for example, and they see that the value is actually quite far from the standard model. So this is not completely understood, but yes, I guess just time will tell, and we need to do, of course, more experiment to see if it really could be that the W meson is so heavy, so much heavier than the standard model expectation value. So there, I will not just go into detail into this slide. So here there are a lot of constraints, as I said, for example, supersymmetry on the left and other exotic signatures on the right. So here you have different models or different possibilities for example, inclusive supersymmetry searches or third generation searchers. And also here, so for example, leptoquarks possibilities or dark matter searches. And on this specific, I must say, these are quite specific searches. If you don't find anything, you can set up limits to one of these parameters. So for example, in this case, if I would see, for example, the leptoquark of the first generation leptoquark scalar, that guy should not have a mass below 1.8 TeV, because that would have mean that we should have seen it. So I don't know if you have any questions yet. If not, I will just continue. I hope this is not too boring. Maybe you have already seen this so many times, but I never know what is the audience. So it is good to do this brief overview on where are we. So with the LHC now, so now leaving a bit behind theory, the LHC is a 20-kilometer long collider ring. It is 100 meters underground in the frontier between Geneva and France. So you can see here, this is just a draw above the surface. Actually, you cannot see this on the surface. You will just see like grass and ships in some of the places here you can see. And here as a scale, you have the airport on Geneva, so you can see the scale of this ring. It has inside 4 main interaction points, which are CMS, ALICE, LHCb, and ATLAS detectors. And at these points, so you will have 2 beams. So for example, in the right plot, you see how the protons accelerate. They first accelerate in a linear accelerator, then go to the PSB to get further accelerator, and the larger the ring, the higher the energies you can achieve by accelerating. So actually these protons get accelerated in these chains from the LINAC to the PSB, then to the proton synchrotron, to the super proton synchrotron, and finally from here you see one of the groups will go this side while the other group will go that side. So there you will have in the LHC, this big ring, bunches of protons going one side and bunches of protons going in the other side. So this will go in two different vacuum pipes. They are accelerated by radio frequency chambers. So this group of protons collide every 25 nanoseconds at these star points. So you have a lot of collisions coming from one run, for example, of the LHC. And at this point, we are starting to having collisions at 13.6 tera electron volts of energy. To give you an idea, typically 1 GeV is the mass of the proton. So you have all this energy. Okay, so once you accelerate them with the radio frequency chambers, these guys would like to go straight if you don't do anything. So there you need 1232 superconducting dipole magnets that actually are used to bend the proton beam. So actually the LHC is not a circular ring, it's actually an octagon. And in the places between two straight paths, there you have the dipole magnets, which will bend the protons in a small part of their trajectory, and then will just keep straight again, and then they are bent again, they keep straight again in this octagonal shape. And doing this, of course, you have two problems because protons are all of positive charge. So first of all, they all want to be apart from each other because of electromagnetic interaction. They are all the same charge, they want to repel. And also once you try to bend them, also depending on the initial conditions, you can also have them dispersed. So that's why we need quadruple magnets to keep the proton in tight bunches. So with this, we pack them together. We just push them first like plates like this and like this. And with this, we just keep them in tight bunches. And just before the start points come, so where the detectors are, so at this point, we just put the beams together, and before the collision, we focus the beams with extra collimators and magnets, and this is to increase the luminosity. So what is the luminosity? It would be the amount of proton-proton interactions that I will have per unit area and time. So if I reduce the area, or also if I increase the numbers of protons per bunch, I will have more instantaneous luminosity, more collisions per, for example, crossing of the bunches. And the integrated luminosity, okay, will be the same, but in total time, integrating over time. And the number of events that will come of any event, it will be the luminosity times the cross section of that event. So for example, with the full run 2, the peak luminosity was 21 times 10 to the 33 inverse square centimeters inverse seconds, and the total integrated luminosity was 139 inverse femtobars. This was integrated over 2015 and 2018. So after 2018, the machine went down. So this was the last run at 13 TeV. And in that period, with this luminosity, we got 40 million billion. So this is 10 to the 15 proton-proton collisions. So we have much data to analyze. So on this point, one of the detectors is the Atlas detector. This is a general purpose detector. This means that it can be used to analyze a quite variety of processes. It's a 25-meter diameter and 44-meter long cylindrical detector. You can see here people to get an idea. These two guys here are the size of people, but actually they are augmented. So these are like 2-meter people. They're very tall. Also here. So here you can have an idea of the dimensions of this. And it is built kind of in layers. I would like to say it's an onion, but it's like a cylindrical onion in which first closer. So here is the beam coming from one side and from the other. Then you just squeeze them and then you make them collide just in here. So from here, initially, you just have the inner detector that is consisted first of the pixel detector and then the transition radiation tracker. Then outside that, you have the calorimeters that measure actually the energy for charged particles. And okay, not also for charge, not only for charged particles, but the electromagnetic calorimeters, the energy of photons and electrons, and then you have the hadron calorimeters that can measure the energy of any hadron. Then you have magnets to bend the trajectory of charged particles, and then outside you have muon detectors, because as I said, muons just pass by without losing much energy. So here I have the same with a cut on the transverse plane, and you see the different distinctive signatures each particle or each type of particle leave in the detector. So for example, we will just start for the matter particles, the electron. The electron is a charged particle. So when it passes through the pixel and the transition radiation tracker, it leaves a track. What does this mean? So the electron comes, interact with the medium that is in there. So there I have an active medium. So the electron ionizes the atom of that medium, and in between the layers, you put a voltage and you take the currents from these ionization cascades, and then you can say, okay, through here, there was something passing by. So that would be the electron in the inner detector. And then you have the electromagnetic calorimeter, which are also several layers of copper and liquid argon. And in this case, every time the electron hits the copper plates and enter into the liquid argon, it ionizes them, it creates cascades, then more particles hit the next layer of copper, and you have then a shower of particles that will lose all their energy within the electromagnetic calorimeter. So both electrons and photons suffer this same in the electromagnetic calorimeters. They are being stopped there, they cannot follow through, all their energy is lost there. So that way you can measure the energy of the electrons and the photons. The difference with the photon and the electron is the photon is not charged, so it leaves no track on the inner detector, and it's also not bent. You see here the trajectory of the electron is bent, and this is bent by the solenoid magnet that is around the outside the inner detector. It has all the inner detector inside this magnet. So the electrons will leave a track, a curved track in the inner detector. Photons will leave no track. They will be stopped both in the electromagnetic calorimeters. So now for neutrons or protons or other hadrons coming out of the collision point. So here is the collision point. For example, neutron is neutral particle, so it leaves no track in the inner detector. As it is not an electromagnetic particle, so it actually interacts with photons, and there is some small electromagnetic interaction, also protons. They mainly lost all their energy in the hadronic calorimeter. So this is a different technology that is meant to stop hadrons due to actually nuclear interactions more than electromagnetic interactions as you have in the electromagnetic calorimeter. So protons also will get bent by the magnet as they have charge. They leave no track in the inner detector, very few energy in the electromagnetic calorimeter, and a lot of energy in the hadronic calorimeter. Then you have a muon. A muon is a charged particle, so actually leaves a track in the inner detector. It loses mostly no energy in the electromagnetic or hadronic calorimeter, also pass through the muon spectrometer, leaving tracks, but it's not stopped there, so it will just continue going. And for neutrinos, neutrinos have no charge, so they won't bend. They also won't leave any charge on the inner detector, neither on the muon spectrometer, and also lose no energy. So they will just fly by undetected. So these are the typical signatures that we can use to distinguish some particles from others. So, as I said, the charged particles are bent by strong magnetic fields. Some particles are stopped in the detector, some pass, and some pass without being detected. And this huge data output that I said, that I talked before, imagine if we have all that amount of collisions, and per collision, you have thousands of additional particles coming out. And in this cascade, for each particle, you have more particles. So actually, you have tons of data that we need to get rid of using this two-level trigger system that actually cleans up a lot of the data, just leaving most of the interesting data to analyze. So the main upgrade, so I think I'm going too slow because of the time, I will just go a bit faster. So during this shutdown, after 2018 to 2022, the detectors and the accelerator prepare for this new run, what we call run 3. So this needs a lot of upgrades and improvements to the machines, as we are going to run with higher luminosity, at higher energy. So everything needs to be tied for this new run. And one of the new things that was put in the detector is a new small wheel. So this is a new muon detector that is actually put before the end cap of the toroid, before this magnet. So it's actually in this forward region. We call it forward, the region that is close to the beam pipe, and we call transverse the region that is here in the barrel of the cylinder. So as you can see here, this is like the upper part of the wheel will be like here, and this is the beam line. And why do we need these new detectors? So here you can see a plot where the first level said that we have all of these events containing muons. The first level trigger said, okay, we have all of these events, but then we do a more strict reconstruction. We match these muons to the inner detector, and then we match them with PT higher than 10 GeV for completely reconstructed muons. And we see that actually the amount of muons were this here. So there were not so many muons in this region of the detector where eta is above 1. So eta is this angle coming from here down to the forward region. So you start here with eta 0, and then the forward region will be eta infinity. So after 1, you see that there are a lot of noise. This means that the first level trigger said, okay, there was a muon here, but actually this was not a good muon. So why is this happening? You can see here, if you don't have this wheel, the green stuff here, muons coming from this place, for example, will be measured by the outside wheel, and they say, okay, a muon come through here, but this muon is coming from any other part, or this could be even particles that are not muons that are being detected. Or for example, this muon had hits here, you see that there's an angle because of they bent. But if you follow this path will not take you to the interaction point. So these muons did not came from the proton-proton collision itself. So having the new small wheel in here, you will only now keep the muons that have a hit in the big wheel, have a hit in the small wheel, and these hits are consistent with muons coming from the interaction point. And okay, with run 2, close to 90% of the muons passing the first level trigger were fake. And the idea is to reduce this amount of muons, keeping the rate higher and having a better sensitivity and better reconstruction efficiency of muons. So the new small wheel, how it is built. So one of the wheels have 16 sectors. You have large sectors and small sectors. So here you see one large sector and a small sector, kind of one behind the other. And each of this sector, you can see it here, has 2 quadruplets of sTGCs that are these new detectors that were built actually here in Chile and in other countries. And each of these have 4 layers of detectors. And then you have micromegas detectors that are other technology. So you can see here that each of these wheels is with more layers, and each layer have several sectors, and you see that this starts to multiply. And each sector, as you can see here, is divided in 3 modules, the 1, the 2, and the 3, going radially up. So Chile was in charge of building all the QS1 sectors. So all the small, the thinner or the closer to the beam line sectors in the small sectors of the new small wheel. So these sTGCs, small strip thinker chambers, are multi-wire ionization chambers. So this is the type of detector. This means we have 2 cathodes up and down here. The first cathode has large division pads, and the other cathode has very thin strips. And then you have wires that are perpendicular to the strips. And in between these, you have a gas mixture. So when a muon passes through, it ionizes the gas, and we connect this to a high voltage. So the ionization electrons and ions coming from the passage of the muon will go through to the pads and to the strips, and we will see there that there's charge being accumulated on these cathodes and anode. So this building with bigger pads and smaller strips on the other side, this is to use the trigger. So once the muon passes through a pad that is a larger area, we will say, okay, now we will look within this pad area, the strips that are important and the wires that are important. And in that way, we can reduce the rate at which the trigger works. So these pads are for fast triggering output, while the strips are for thin and more precise precision measurement of the position of the muons. Then the output is passed to these FPGAs, and this design allows for 100 to 300 microns spatial resolution for the muons. So actually, it's quite a very good precision. So each layer has these front-end boards. Each front-end board, okay, depending on if it is at sTGC or micromegas, what is the front-end board? So I will just concentrate on sTGCs. You have strips, front-end boards, and pads, front-end boards that are also for pads and for wires. And each of these front-end boards have these VMM ASICs. So that has each. So here you see ones for the SPFEB with 8 ASICs, and for the PFEB you have only 3 ASICs, and each of these ASICs have 64 channels. So if you have 32 sectors, 8 layers per sector, 6 front-end boards per layer, 3 or 8 VMM ASICs per front-end board, and each of them have 64 channels, at least for sTGCs, and then for micromega something similar, you have around 3 million channels individually that needs to be calibrated. So this is not an easy job. So what is that I'm calibrating right now? I am trying to calibrate the AETC or the TDO amplitude. So basically the VMMs are linear electronics. This means that the output signals is directly proportional to the input signal strength. So to do this, we always use this analog to digital converter. So we need to take an analog signal and transform it into digital. And one way to do this is using the TDO approach. So the TDO, what do we do? So first, if the signal comes, we start taking time where the peak comes. And as soon as we start taking the time, we do this TAC ramp, which is, so TAC means actually time to amplitude converter. And we start filling a linear plot until the pulse is completely gone. So this is, you should know, have a time at which you know that the pulse will be over. And then the TDO will be the amplitude of this tag ramp. So here I have I will put it again, 2 pulses. So this is not exactly from the detector, are separated. And the guy is moving just one screw maybe to put these pulses away from each other in time. And you will see now, I will just repeat it, that the amplitude of the tag or the TDO is down. So the more split they are in time, the higher the amplitude you have in this plot down here. And this can be used by, for example, filling energy in a condensator. So even though it's not completely linear, once it passes the first threshold, it goes linear until it starts filling up. So there we can convert any analog time into this amplitude, which is digital, just one value. So for each channel, you have different ramp slopes, and we need to have an accurate calibration to achieve precise measurements. So I will just go here without not much detail. So here is a typical TDO distribution for one channel with many events. So this should look like a double sigmoid function, but of course we have noise. This is not perfect. So what we need is to fit this function with a rising value, an average, and then a falling value. So to fit this kind of function is not trivial, because we need to have initial values A, B, and C close to the real ones, so the fit converges. So the first approach was to just take the whole range of the TDO, go to the middle, make a window in the middle here of 50 bins, take all these channels here, all these bins here, get the amount, the quantity, so all here near 25 or some are higher, and we add them together, and that will be the average for us. This will be like the initial A value. And then so then I going up from 0, going up, and then as soon as I have a bin with content more than 50% of the average, so here maybe I will say, okay, this will be my initial A value, so B value, so the rising. And then again, I go from up going down, and then the last bin with content above half of the average, I will consider it as my initial value for C, for the falling of the TDO distribution. So this was working very nicely from 1,633 channels, because at the beginning I was only working with a very subsample of only one quadruplet with 4 layers, only 6 channels. Only for 6 channels the fit failed, and looking at this, I was realizing that some distributions were thinner. So you see here, I go to the middle, I put these windows, but I'm taking bins that have no entry. So the average is getting lower. So the average here should not be close to 20, the average would be close to 25. So then I just get the initial B and C values. So this is the second approach, trying to fix this kind of fits that are buggy, because you can see here that the fit is not actually converting to the distribution. And I say, okay, I will just get the initial B and C values with the first bin that has content above 5, just a fixed value, just to test. And then I count 9 bins up, 9 bins down, I will take the average there. So as you can see, the fit, this procedure fixes this channel, and you can see now that the distribution and the fit are much close together. But bad news, I did that, and now from the 6 failed fits, I have 77 fails. So the idea is not to do this one by one. I want to have a procedure that does all of them and try to have the least failed fits possible. So I am realizing that I am saying, okay, get me the first bin above 5, and the last one, and you see here, this says, okay, the last bin above 5 was in 200, and this is not true. I don't see, for me, the last bin above 5 is this one, not this one. So then I realized that there was a stupid smoothing algorithm on this histogram, the real histogram was looking like this, more noisy. And you can see all of these little bins here that actually I should not look at because this kind of noise. So the first bin above 5 was this one, and this was taken for the initial value before the fit. So this is why the fit is not converging. So I cannot just do that. So I did a third approach. I put here a star because not the third. I was trying a lot of different possibilities. So now we just get the bin with higher entries. I get the average of all the bins that have content above 20% of this higher value. And then I slide with a 3-bin window. So I take 3 bins here and start going up. And I ask if these 3-bin windows have an average of content above half of the maximum average of the total average. So I do that to avoid having this, because here, okay, this has more than 5, but if I add it with the neighbor bins, like 3 bins, this will have 0. And if I get the average of these 3, this number will go much lower and won't be above 20% of the average. So this actually helped a lot to kill these problems. And actually from, I only get 3 failed fits in this way. And also I was not only fixing that, but I was finding very strange and buggy channels like these ones, channels that actually don't have the correct shape. And if you see the original without smoothing histograms, you see things like this. So these channels start having values, then it's completely dead and have a huge outlier, and then it continues. So here, this was the only bin above 20% of the average. So the average was get to this bin. So this, of course, also needs to be fixed. That I did. But the idea here is not only to fix it, but also to be able to find these buggy channels and to maybe we can, I don't know, set a higher thresholds for these or reduce the noise for these channels to make them behave the way they should. Remember, this is all coming from the output from a detector. So this new approach is helping me to find the proper values, and it's also helping me to get buggy channels under control. So additional findings, besides that, I have seen these channels with lots of noise here that are kind of strange, and also these outliers on the last bin. So all of this was just getting written into a database to look more closely to these channels. But for all the other channels, the idea is to have automatically the rising, the average, and the falling values automatically calculated. So the last test I did with the algorithm was already using a collision data at 900 GeV in the pit. So this is already with the new small wheel installed in the Atlas detector. So this is starting to get complicated because the code was only working for, as I said before, a very small quadruplet with 4 layers and just 1 sector. So now I have all the channels that are being added. And actually, in this run from 2,250 channels, I have only 25 failed, which is actually quite good. But of course, could be less. But the idea is to look at these 25 failed channels and see what is actually happening. And of course, as always, this is a lot of computing. The channels were mixed, the IDs between the micromegas and the sTGCs. And as you have millions of channels, this is always a problem to debug. Okay, that's what I'm doing right now, trying to run for the full 2 wheels with all the sectors and all the layers included and have the least fail fits possible. So I know I'm kind of past the time, but just very quickly, how would I use this to find new physics or physics beyond the standard model? So usually, for example, these hints that I said before with involving lepton flavor, unitarity, or universality violation, with these B quarks and involving leptons, led to many searches, but most of these searches are for heavy bosons. and they are doing searching for bumps, as we show them in the plots of the Higgs. So you see the distribution and you see a little bump and you say, okay, there's a particle there that we don't know. But if the masses are too high, so if these set primes, extra set bosons, so extra maybe even further interactions, if the mass is too heavy, the sensitivity is lost because you have less cross section and less number of events, so you cannot do a very nice analysis. So the idea is to study the interference of possible heavier bosons in the kinematic distributions, but not just search for bumps in the invariant mass distributions. So for that, we can use higher dimensions operators, in which you use, for example, an effective field theory, integrating out this boson and having just one regular or coupling that, of course, will capture all interference effects that could be, but it will remain insensitive to the specific nature of the boson. So this is called the contact interactions between two leptons and two quarks. So this is kind of a la Fermi. And you have possibilities of having, so there is already one analysis done with BSLL contact interactions, completely forbidden in the standard model. And as nothing was found, they are putting an upper value of lambda over, so this is G actually, oops, lambda over G. Because this is how we, lambda is the scale and G is just a square root of 4 pi. So that value is less than 2 or 2.4 TeV in the case of electrons and muons, as you said. As I said before, you can put upper values to things that you have not found. So the idea now is to add 3 additional processes that is not BSLL, but BLL, TULL or TT bar LL. And of course, for all these possible channels, you have 2 opposite sign leptons and same flavors, i.e. or mu mu, and with at least 1 or 2 B-jets. High values of MLL. The idea is to start optimizing signal regions for the different possibilities. And these possibilities depend on what it is. So here in the next plot, you see here the BLL possibilities. Depending on how you got them created, then you can have direct BB annihilation into 2 leptons. So this will have no extra B-jets. But if this is produced via gluon B interaction, then the 4 coupling, the 4-leg coupling that I showed would be here. And in this case, you will have the 2 leptons and 1 extra B boson. Or if you have gluon fusion, then you have 2 bosons coming from the incoming gluons. And then here you have these 4 vertex, and then you have the 2 leptons. So you have 2 opposite sign, same flavor leptons plus 2 B-jets, 1B and 1B bar. So depending on which of these effective theories you use, you will have different amount of and different signatures for the outcoming particles that this is what we search for, and this is what we build our signal regions to search for. So in summary, the standard model is the most precise model, but yet we know already it's not the ultimate model. So sTGC detectors were installed in the new small wheel as part of the Atlas muon detector. This was a huge milestone to Chilean development in particle physics. This is the first time that we built. So we designed, we built, and we sent there, they put it there, and we're now testing it. So this is the first time that Chile is gone like the full chain from design to analysis. So accurate calibrations are essential to achieve precise time measurements. One very difficult thing for me, coming also a bit outside the research and just starting now, was very difficult to find documentation, because this is of course not written in any book. You just need to navigate through talks and talk to people, just send emails. So this is quite difficult to know what amount of channels there is, and all of this is not easy. So I show you TDO calibration examples, also some algorithms and some of the problems, just to get an idea of what I'm fighting every day with. I'm now fixing the algorithm to minimize individual handwork and to make it work over the full amount of channels for both technologies. And I showed you very quickly prospects for high mass Rayleigh processes using leptons, and I'm trying to aim for the electron muon asymmetry. So sorry because I'm a bit out of the time, but that's it. I hope you liked it.
Yeah. Thank you very much, Pedro. It was a wonderful talk. So does anybody have any question for Pedro?
Make a line, make a line.
So I would like to start with maybe a naive question because this is not my area, but these pieces that you were constructing, these pieces of the detector of the small wheel that you constructed here in Chile, that we were constructing, how much time does it took to construct them, and where does the funding to build these systems come from?
So actually, I'm not sure about the time, but the design was even like 10 years ago, I think, at least the design for the new small wheel. Also, not all the detectors were built in Chile. There are some other parts of the detector built elsewhere. And also, it's quite difficult to say how much people was involved because many students has passed by and people has gone. So actually, I'm coming kind of new now here, but I know that this is at least a minimum of 5 years, I would say, least.
Wow.
Chile. So and the funding comes mainly from CONICET and ANID in each cases, and also from the university and where people works. So yeah.
Right. Perfect. Oh, okay. Anybody? Anyone? This is the time. So I have a more general naive question, but this is completely naive and general. So would it be possible to use the LHC as an electron-positron collider?
So actually, before the LHC, I don't know if you know that there was LEP in the same channel.
Yes,
so in the same channel, you had an electron-positron accelerator, but you had different magnets. So with the magnets that you have now, they are thought to have just proton-proton collisions, even though you can also accelerate, for example, lead or lead proton, even you can have gold collisions. So with a few tweaks, you could do that. So now the detectors and the accelerator is not thought to be electron-positron collider, because mainly, for example, as you have seen, there are a lot of noise coming from hadronic radiation. And so that's the detectors are built for that. We need to clean that. But an electron accelerator is much more clean. The signature of the outgoing particle, you don't have all this hadronization jets and noise coming from hadronic collisions. So actually, they are thinking on building the next generation collider in CERN. This is just a project, so this will have like 100 meter long instead of 32, so it would be actually bigger ring. And they want to start that with an electron-positron accelerator, and then once that is done, they will use again the ring to do a proton collider. So
perfect.
You could, some parts you can reuse and some others you just build them new. So at the moment the LHC is thought for protons, but at least the tunnel and all their capabilities could be actually eventually used for an electron-positron collider.
Right.
The detectors then should be different. So I think now the detectors are thought for hadron colliders.
Yeah, they're optimized for
Exactly.
detection and okay. Well, thank you. So if there is no more questions, I would like to thanks again, Pedro, for the talk, and thanks everyone as well. and we'll see each other in the next seminar. So thank you.
Okay, bye. See you
Bye.
next
Bye,
seminar.
everyone. Thank you, Pedro. Bye, everyone.
Thank you.
Thank you.